Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
The ultimate question. So one we've all thought about, late at night since we were kids. Where did we actually come from?
And we're not talking philosophy today.
No, not at all. We are tackling what might be the hardest scientific problem out there. How a bunch of non-living chemistry, just molecules, made that incredible leap to become biology, to become the first living cells.
And we're diving into a really provocative answer to that question. The hypothesis we're analyzing today is that life on Earth, and I mean everything, from the trees outside your window to you, it didn't actually begin here.
No.
It was delivered. It hitched a ride, a very rough ride, on a meteorite, all the way from the planet Mars.
The idea that we are fundamentally Martians is it's thrilling. It's the ultimate cosmic plot twist.
It absolutely is. And look, while most scientists in this field still favor life starting right here on our own planet, you have to look closely at the timelines, at the constraints. The Martian transfer idea is still an intriguing hypothesis for one big reason.
And what's that?
It solves one enormous problem, but in doing so, it creates a whole bunch of others.
So that's our mission today. We're going to test this idea against some pretty harsh realities. Planetary formation, space physics. We've been looking at recent analyses of the cosmic clock, geological records, even some amazing genetic reconstruction of our oldest ancestor.
LUCA, the last universal common ancestor.
Exactly. So we need to know, does the timing pressure on Earth force us to look somewhere else, like Mars?
Yeah.
Or is the journey from Mars just too impossible to even consider?
There are really two core conflicts we have to resolve for you. First, was the window of time for life to start on Earth just too short? Because if it was, the Martian idea suddenly gets a lot more compelling.
Right.
But second, even if life did start on Mars, could it possibly have survived that brutal trip through space? If that journey is impossible, the whole hypothesis just collapses.
Okay, let's unpack this. I think we need to start by setting the stage and looking at that cosmic clock. Let's see which planet really got the head start in the race for life.
When we talk about origins, you have to anchor yourself in deep time. I mean, really deep time. We start around 4.6 billion years ago.
Okay.
That's when Mars, because it's smaller and a bit further out, cooled down and solidified into a proper planet. Earth came just a little bit after, around 4.54 billion years ago.
So Mars gets about a 60 million year head start. Now, in geological time, 60 million years doesn't sound like a lot, but what does that window mean when you're talking about the chemistry of life?
Oh, it's crucial. That 60 million years is absolutely critical because of what has to happen in those first steps. We're talking about incredibly complex molecules learning to assemble themselves,
Right, the first building block.
Exactly, the first large organic molecules that could replicate, that could carry out some kind of metabolic function. Now, these processes, they might be fast under perfect conditions, but they need stability. And the longer a planet is cool and stable, the higher the odds are that this will happen.
So that 60 million year lead meant Mars was potentially brewing life while Earth was still a chaotic, half-formed mess.
That's the idea. And it's so important to remember that right after they formed, neither planet was welcoming at all. The key thing here is that the energy from their formation meant their surfaces were initially molten. Just global oceans of magma.
You can't start life in an ocean of magma.
No, you definitely cannot. Life can't start when the surface is liquid rock. So both Earth and Mars had to cool down, let that heat escape, and allow a crust to harden on the outside. And that process, that's the real starting line for habitability.
And once that cooling started, the two planets went down very different paths.
Wildly different. And this is why early Mars is such an appealing place to look for life's origins, especially when you compare it to the frozen, irradiated desert it is today.
So paint that picture for us. What did the red planet look like 4.5 billion years ago that makes it such a strong candidate?
What's really fascinating is that the evidence suggests early Mars was maybe even more suitable for life than early Earth was.
More suitable.
Yes, it had all the critical pieces you need for life to start independently.
Give us the shopping list. What do you need to start life from scratch?
Okay, first, and this is non-negotiable, early Mars had a protective atmosphere. It acts as a shield against, harmful radiation from the sun, but more importantly, it creates enough pressure.
Pressure for what?
For liquid water to be stable on the surface, without that atmospheric pressure, water just boils away instantly into space.
And we know for a fact Mars had that water.
Vast amounts of it. We see the evidence today in the ancient riverbeds, the deltas, the geological signs of oceans, rivers, and lakes. So we had the essential solvent for chemistry to happen.
Okay, so atmosphere, water. What's the final piece of the puzzle?
Energy and chemical complexity. Early Mars was almost certainly geothermally active.
And geothermal activity, why is that so critical? Why can't life just, start in some quiet little pond?
A quiet pond is too dilute. It's too calm. To get life started, you need to concentrate the ingredients, you need heat, and you need mineral catalysts. Geothermal places like deep-sea hydrothermal vents or hot springs on land, they are the perfect cradle for life.
So they're like little chemical factories.
They're perfect. They have high temperatures for fast reactions, a constant supply of mineral-rich water that concentrates the organic stuff, and a source of chemical energy like hydrogen or methane that the very first cells would have needed to eat.
So if Mars had all of that, which it seems it did,
then life could, in theory, have gotten started there very early, maybe right after it formed, around 4.6 billion years ago.
So to recap, Mars gets a head start, it has all the right ingredients, it's ready to start cooking up biology. But then, back on Earth, something so catastrophic happens that it completely sterilizes the planet.
And this is the dramatic difference between the two stories. We're talking about the Theia impact, Earth's great biological filter. Around 4.51 billion years ago, just 30 million years after Earth even formed, a planet the size of Mars, which we call Theia, smashed into the proto-Earth.
That is just, it's staggering. It's hard to wrap your head around that kind of collision.
The best way to think of it is not as a crash, but as a cosmic reset button. It was hit with planetary force. The energy released was so immense it didn't just melt the crust. It re-vaporized and melted both planets.
Both planets.
Both Theia and the proto-Earth. They basically became one big, superheated blob of molten rock and gas, which then eventually separated to form the Earth we know today and the Moon.
And that kind of energy means total, absolute sterilization.
Absolutely. The temperatures would have been thousands of degrees. If any simple life, any self-replicating molecules that started on Earth before that, our sources are clear, they certainly would not have survived it.
It just boiled the oceans, vaporized the atmosphere, and liquefied the entire surface.
Earth was scrubbed clean.
So Earth hits its biological reset button 4.51 billion years ago. Our story of life can only begin after that, after the surface cooled down enough to hold water again. Meanwhile, what's Mars doing during all this chaos?
And this is the critical point. This is the real strength of the Martian origin idea. The contrast is just fascinating. The early solar system was a violent place, but Mars, for whatever reason, maybe it's orbit, maybe just cosmic luck, it didn't get hit by anything big enough to cause a global planet-sterilizing remelting event.
So no cosmic reset button for
Yep.
Mars. Why not? Why didn't it suffer the same fate?
The main reason is probably its size. It's smaller. Now, that might sound like a disadvantage, but in this case, it might have saved it. Because of that relative stability, if life got going early on Mars, say between 4.6 and 4.5 billion years ago,
It could have just kept going.
it could have continued evolving without any major planet-killing interruptions for at least 500 million years.
500 million years of uninterrupted evolution.
Yeah.
Compared to Earth, which was basically sterilized right after it formed, that's a monumental lead.
It's a huge lead. It means Martian life would have had time to optimize its biochemistry, to diversify, to fill different ecological niches, and maybe most importantly for this whole hypothesis,
To get tough.
to become incredibly hardy, a necessary trait if you're going to become a cosmic hitchhiker later on.
But Mars isn't a paradise now. That 500 million year window must have closed. What happened? What signaled the end of habitable Mars?
The clock was definitely ticking for Mars, and again, it was mainly because of its size. After that first crucial 500 million year window, the internal engine of Mars, its core, it cooled down too quickly and just stopped.
And that killed its magnetic field.
Exactly. It caused its essential protective bubble, the magnetic field, to collapse.
But wait, why did Mars lose its field so fast when Earth still has a really strong one? Was being smaller just an inherent cosmic disadvantage?
That seems to be the key. We think Mars, being smaller, just lost its internal heat much faster. Earth is bigger, its core is different, and that allows our liquid outer core to keep churning away, generating a protective magnetic field.
And once that shield is gone, the atmosphere is just doomed.
Pretty much. The solar wind, which is this stream of high-energy particles constantly blowing off the sun, it could then just attack the Martian atmosphere directly.
And it just stripped it away over time.
Exactly, molecule by molecule over millions of years. And that was the end of Mars as a hospitable world. Without the atmospheric pressure, the liquid water either boiled off or froze solid, and the surface was left exposed to two major dangers.
Which were?
Freezing temperatures and intense, lethal doses of ionizing radiation from space.
So any life transfer from Mars to Earth had to happen early. Within that first 500 million years, while Mars was still wet and warm and could actually support life.
That's the window.
Okay, so now let's pivot back to Earth and look at the other side of this timing problem. How fast did life manage to get going here after that great sterilization?
This brings us right to the core challenge for the Earth-only idea. We're looking for that moment that life sprang back into existence after the Theia impact. And to do that, you have geneticists and paleontologists working backwards from all known life today.
So we're moving past the Great Reset now, and we're focusing on the first definitive evidence of life here on Earth. And that evidence leads us to a crucial invisible ancestor. LUCA.
LUCA, the last universal common ancestor. And it's really important to get this right. LUCA is not the very first cell.
No.
It's the microbial species from which all life today, everything is descended. It's the root of the family tree, but that means it was already part of a mature ecosystem. There were other branches below it that died out.
And there was a recent study that's critical here, right? Because new genetic techniques have pushed LUCA's timeline back, way back, making Earth's evolutionary speed limit even tighter.
That new timing is everything. Scientists used really sophisticated genetic analysis. They looked at what are called conserved genes that are so essential to just basic cell function that they haven't changed in billions of years.
And from those, they could reconstruct LUCA.
They could reconstruct its biochemistry and, critically, figure out how old it was. This detailed genetic work suggested that LUCA lived 4.2 billion years ago, much earlier than we used to think.
Let's just pause on that for a second. Reconstructing an organism that lived 4.2 billion years ago, when all you have are its distant descendants. That sounds like a miracle of science in itself.
It's a remarkable piece of deduction, really. Because genetics works on mutation rates and comparisons, finding those deeply conserved genes lets you trace everything back to that single node. And the fact that we can place LUCA at 4.2 billion years ago tells us something huge.
What's that?
That the life we all come from was already well established very shortly after the Earth cooled down from the impact. And that dramatically compresses the time available for that initial spark of life.
Okay, let's calculate that timeline precisely. This is where the whole idea of the breakneck speed of life on Earth comes from.
Okay, we need our two fixed points. The moon-forming impact, the big sterilization event that happened 4.51 billion years ago.
And LUCA, our universal ancestor, was alive and kicking 4.2 billion years ago.
Right.
So we subtract 4.2 from 4.51, and that leaves us with only 290 million years. That is the absolute maximum window for non-living chemistry to become living, self-replicating biology, and then diversify into a whole ecosystem.
And here's the context that really puts the pressure on. Remember, LUCA wasn't the first organism.
Right, it wasn't alone.
No, according to our source material, it was just one of a multiple species of microbe existing in tandem. They were competing, they were cooperating, they were fighting off viruses, surviving a really harsh environment.
So you're saying life had 290 million years to go from, what, a few basic molecules to a sophisticated ecosystem with a common ancestor. To put that in perspective for everyone listening, 290 million years is about the time separating us today from the very first reptiles. And life had to start from scratch.
It's the sheer complexity that has to arise that makes the timeline feel so incredibly tight. You need a series of statistically unlikely steps to happen. You have to get the prebiotic molecules concentrated. You need to form RNA or DNA. You need to wrap it all in a cell membrane. You need to kickstart a metabolism.
And to do all of that and then diversify into multiple species in under 300 million years.
That is the core question. Was that enough time?
And if the answer is no, if that's just not enough time, then the Martian hypothesis suddenly looks really, really good. It's basically saying, don't worry about it, we just imported the finished product.
Exactly. But before we get to that, let's look a little closer at LUCA itself because its characteristics tell us a lot about what early Earth was like.
Okay.
Its reconstructed genome suggests it didn't use sunlight. It lived off of chemical energy molecular hydrogen or simple organic molecules.
Which points directly back to those geothermal environments you mentioned.
Yes. It suggests LUCA's habitat was probably a shallow marine hydrothermal vent or maybe a geothermal hot spring on land. Again, these are the high-energy, chemically rich places that we think are perfect for starting life.
The fact that LUCA was already living in these really intense places also tells us something about the defenses it needed just to survive on early Earth.
It did. LUCA had some pretty sophisticated biochemical machinery to protect it from two major dangers. First, high temperatures, which makes sense for a hot spring or event.
And second,
intense UV radiation. Early Earth didn't have a proper ozone layer yet, so anything near the surface was getting blasted by the sun, which just shreds DNA. The fact that LUCA had machinery to deal with this confirms that its environment was brutal.
but even with all of LUCA's adaptations, that 290 million year timeline still feels tight. And this is where our source material brings in a direct perspective from an expert in the field.
That's right. One of the researchers offered a sort of counterintuitive take on this, saying that their professional hunch, would be that 290 million years is actually plenty of time.
Plenty of time.
Plenty of time for chemical reactions to produce the first organisms and then for biology to diversify and become more complex.
So this view, coming from someone who studies this for a living, suggests that maybe the timeline pressure isn't the hard barrier we think it is. Maybe abiogenesis, the start of life, is actually a much faster, more probable event than we usually give it credit for.
And if that's true, if chemistry just naturally clicks into biology relatively quickly, then the Martian hypothesis loses its main selling point, which was time.
Right. But it still leaves us with this profound choice. Was it a rapid miracle happening here, or was it a massive, unprecedented feat of physics to get it here from somewhere else?
And that is the next big hurdle.
Okay, here's where it gets really interesting for me. Because even if we say the timeline on Earth is tight but maybe manageable, the Martian origin idea has to get over the ultimate barrier.
Sure.
The physics of survival.
Right. This idea, which is sometimes called lithopanspermia, it neatly sidesteps the timing problem. It suggests Martian microbes traveled here on meteorites and arrived just as Earth was becoming nice and habitable after the moon formed.
But the massive counter-argument is, could anything, even the toughest microbe imaginable, actually survive that journey?
We are talking about taking a tiny single-celled organism, strapping it to a rock, and flinging it across interplanetary space. This is not a gentle cruise.
Not at all.
It is a journey through a biophysical gauntlet. To get from Mars to Earth, a microbe has to survive a chain of 5 extreme, often lethal conditions. And there's nothing in LUCA's genome that suggests it was adapted for space travel. It was adapted for heat and UV light on Earth, which is a whole different ballgame.
Okay, let's break down that 5-stage gauntlet of interplanetary trauma. What are the challenges, step by step?
The very first step is the most violent, initial ejection. The life form has to survive a massive asteroid impact on Mars's surface. This means enduring a huge shock wave, the intense heat from the impact, and the sheer acceleration you need to hit escape velocity and get blasted out of the Martian atmosphere.
What kind of forces are we talking about here?
Catastrophic forces. The acceleration needed to eject a rock from Mars means the microbes inside are subjected to thousands of Gs. You know, a fighter pilot usually blacks out around 9 Gs.
So we're talking about forces that would just crush anything we know.
Instantly. It would vaporize soft tissues. Only a dense microscopic structure, maybe already encased deep inside a rock, has any chance at all of staying intact.
Okay, so if it somehow survives that initial blast, it's immediately thrown into the void.
Exactly. Stage 2 is vacuum travel and radiation bombardment. The microbe has to survive the absolute vacuum of space, which means total dehydration, while also being constantly blasted by cosmic rays.
Now, why are cosmic rays so much more dangerous than the UV radiation LUCA was dealing with here on Earth?
UV radiation is harmful, but it's pretty low energy. Cosmic rays are high-energy particles, protons, atomic nuclei moving at nearly the speed of light. They're what we call ionizing radiation. When they hit something, they literally rip electrons off atoms. They shred DNA. They destroy proteins.
And on Earth, our atmosphere and magnetic field protect us from that.
They do. In space, that shield is just gone. The cumulative dose of radiation is lethal.
And the trip isn't a quick hop across the solar system.
No, that's stage 3, duration. The calculations show that a meteorite journey from Mars to Earth would take, at a minimum, the best part of a year. But it could be tens of millions of years, just depending on the orbital path it takes.
So it's exposed to that radiation and cold and vacuum for at least a year, maybe millions of years.
Right. Survival depends entirely on the microbe's ability to go into some kind of suspended animation, like forming a spore.
Okay, so let's say it survives the ejection, the vacuum, the radiation, the long journey. Then it has to deal with a fiery arrival.
That's stage 4, atmospheric entry. The meteorite hits Earth's atmosphere at incredible speed. This creates intense friction and plasma temperatures that incinerate the outer layers of the rock.
So even if the outside is vaporized, the inside has to stay cool enough to protect whatever's in there.
Ideally under 100 degrees Celsius, yes.
And then finally, it's not going to be a soft landing.
No. Stage 5, final impact and landing. The microbe has to survive a second massive shock event when it hits the surface. And critically, even if it survives the crash, it has to land somewhere it could actually live.
Landing in a nice, warm hydrothermal vent would be perfect. Landing on a glacier or a dry piece of rock would be fatal.
Precisely.
That is just an astonishing list of required miracles, and the source material seems to be pretty skeptical about this whole sequence.
It states it pretty plainly. The chances of all of this seem pretty slim to me. The author concludes that the transition from chemistry to biology happening right here on Earth seems far easier than the Martian scenario.
Because the Martian scenario swaps one big problem, the tight timeline, for a whole chain of colossal problems in survival physics.
Exactly. It requires life to arise, then evolve the ability to withstand stellar violence, then survive for maybe millions of years, and then successfully wake up on a whole new world.
So what are scientists looking at to make this journey even remotely plausible? I mean, we have to be looking at the toughest life forms we know of.
We are. The survival studies all focus on what we call extremophiles. Only the absolute hardiest microorganisms could possibly survive this. We're looking for life that has evolved some almost sci-fi level protective mechanisms.
Give us an example. What's the poster child for this kind of resilience?
That would be a bacterium called Deinococcus radiodurans. It's often nicknamed Conan the bacterium.
Like that.
Because it can withstand massive doses of ionizing radiation, hundreds of times more than a human can. And it doesn't do it by blocking the radiation. It does it by having incredibly efficient, redundant DNA repair kits inside its cells. So its existence hints that life can evolve ways to survive that deep space radiation of stage 2.
But even Conan the bacterium has to handle the total dehydration over time and the intense heat of atmospheric entry.
Right. And that requires a second critical ability, forming spores. Some bacteria, like bacillus, can go into this dormant, highly protected state. They basically dry themselves out and lock their DNA inside a tough protein shell. And they can survive like that for thousands, maybe millions of years.
But even the toughest spore is going to get vaporized by the impact or the atmospheric entry unless it has some kind of protection. How do we solve the heat and shock problem?
This brings us to the crucial get-out-of-jail-free card for this hypothesis, the meteorite shield. The idea is that if a whole population of these microbes were trapped deep inside a large enough meteorite, they could be protected from the worst of it.
So the rock itself acts as a heat shield and a radiation shield.
The bulk of the rock acts as an ablative barrier. It absorbs the shock, it protects from some radiation, and most importantly, it dissipates the heat of entry. The outer layers burn away, but the inside stays cool.
How big does the rock have to be?
It has to be big enough. Computer simulations support this idea. They suggest if a rock is more than, say, a couple of meters in diameter, the core on the inside can stay thermally stable during that fiery plunge through the atmosphere.
But what about the duration? The cumulative damage over millions of years from those high-energy cosmic rays, that still seems like the biggest hurdle, even with a 2-meter rock shield.
That is the ultimate limiting factor, and it's why there's so much ongoing research here. There are lab experiments and simulations trying to test this right now, trying to figure out how quickly radiation damage builds up, even in a shielded, dormant spore. It's really a race between biology's maximum possible resilience and the harsh, undeniable physics of space.
Okay, so we've laid out the whole case. The geological time constraints, the advantage Mars had early on, the blinding speed of life's evolution here on Earth, and then the staggering physical hurdles of the journey itself. So, where do we land? Are we the Martians?
Well, you have to hold a balanced view. The hypothesis is plausible, and the reason it's plausible is because early Mars was an excellent incubator for life. It was wet, it was stable, and it had a 500 million year head start.
A huge head start compared to Earth's chaotic, sterilized beginning.
Exactly. Mars had the time advantage while Earth had the speed challenge, that maximum window of only 290 million years to go from chemistry to a complex ecosystem.
But the evidence against the Martian origin is pretty significant.
It is. First, you have the incredible difficulty of that interplanetary journey. You have to survive 5 separate near-lethal trauma events. And second, you have the fact that many experts in this field still lean towards the idea that 290 million years is enough time for life to start here.
So what does this all mean? The Martian origin hypothesis, the idea that our roots are red, it remains this really powerful and important thought experiment. It forces us to examine the limits of evolution and abiogenesis, but it faces such monumental challenges from physics that it's far from the leading theory.
Right. We're left choosing between what looks like a very rapid early miracle here on Earth or a staggeringly difficult feat of survival physics to get it here from Mars.
And as we close out, there's one final profound thought that our source material raises that kind of puts the whole idea in context.
Yes. This really forces you to think critically about how efficient this whole process of panspermia could be.
We've established how hard it would be for life to get from Mars to Earth. What about life getting from Earth outward?
Exactly. If life successfully made that journey from Mars to Earth on a meteorite within the first 500 million years of the solar system, a time when conditions were chaotic and impacts were common,
then why hasn't that process happened again and again from Earth across the whole solar system in the 4 billion years since?
Earth has been teeming with incredibly hardy life for 4 billion years. We are constantly having impacts that eject rock from our own planet out into space, carrying microbes with it. If the journey is genuinely plausible, we should have found definitive evidence of Earth life spreading to the moon or even contaminating Mars today.
And the fact that we haven't found that evidence.
The fact that the search hasn't yielded anything definitive raises a really critical question about how viable that original Martian transfer really was in the first place.
Maybe the transfer is just too difficult. Maybe the conditions required for that chain of 5 miraculous survival events are just so rare they've effectively never happened.
And that leads to an important final thought. Maybe we're not the Martians after all. Maybe the simplest explanation, that life began right here, is also the most resilient one.
Fascinating. Whether we're cosmic hitchhikers or the product of breathtakingly rapid evolution right here at home, the story of life's beginning is truly the ultimate origin story. Thank you for joining us on this exploration of our cosmic past. We really encourage you to keep thinking about these implications of planetary history and biological resilience.
And remember, critical thinking is essential when you're confronting questions on this scale. We've given you the data points. Now, keep questioning your assumptions about the universe. We'll see you next time.